moving from these theoretical descriptions of atmospheric circulation, talking about how the real atmosphere works. And this allows us to bring in the continents. And we'll start by looking at the circulation patterns in terms of mean sea level pressure. So mean sea level pressure is just surface pressure that's been reduced to mean sea level. Okay, so in Moscow, the surface pressure that we might measure in this room, the amount of air mass pushing down, might be something like 925 millibars, but we are 800 meters above sea level, so we have to reduce that. These are the patterns that show up. These are climatological normals, so technically they're actually taken for the time period of 1959 to 1997, so it's a long-term average. And we see a couple features in here. There's two things that are plotted. One are in color, which show the sea level pressure. So the blue colors are indicating regions of low sea level pressure. The oranges are showing regions of high sea level pressure. And then if you look close enough, you also see vectors. And those are the wind vector components. That's the surface wind speed. Okay. And this simulation here is for, it's not a simulation, these are just an animation for the 12 months of the year. And so we can see a number of features that we talked about last time. First of all, what you can note is the seasonal reversal in pressure between the mid-latitude oceans versus the mid-latitude land masses. So in the summer months, what we see is actually high pressure over the oceans, low pressure over land, whereas in winter, the opposite happens. So in winter, we generally see relatively higher pressure over land, relatively lower pressure over the oceans. Do we recall why that is? Why would there be lower pressure over the oceans, relatively lower pressure over the oceans in winter than over land? They retain the heat, yeah. So land masses cool down dramatically in wintertime, and cold air, if we ignore everything else, that cold air mass will generate a high pressure associated with it. You see some really strong highs that develop over Siberia. You'll notice here the Antarctica. For the most part, Antarctica has predominantly very high pressure. Adjacent to Antarctica is the Southern Ocean. By Southern Ocean, I'm referring to this uninterrupted band here of latitude, right? And what you see is actually permanently low pressure, surface pressure there in the open ocean. So this is a feature that is quite dominant. It actually persists for the entire year, although it varies in intensity. And you can see here a couple of the other features that we've talked about. If you look in the subtropics, over the ocean basins, right, what you'll notice is the trade winds, so winds that are blowing equatorward and also westward. So those are pretty prominent. And where they meet, that forms the ITCZ, the Intertropical Convergence Zone. Other features that we can note here, if we look at India and Asia, what we'll actually notice is that there is a dramatic reversal in winds by season. So if we go into the summer months like here, what you'll actually note is a development of very low pressure over India, over the Himalayas, etc. And what that ends up generating is a pressure gradient force. So during the summer months, we develop low pressure over the landmass, higher pressure over the ocean, right? And that's just all due to the thermal imbalance. And that drives onshore flow. So you'll notice there's onshore flow. The winds are directed from the south to the north. That's bringing warm air that's been hanging out over the Indian Ocean. It's warm, it's moist. As it advects and moves over the continent, you develop the monsoonal circulation. I think that's the slide after this one. Let's actually go right to that here. So here we're looking at the climatology of sea level pressure and contours and the wind speeds in vectors for January and July, focusing here on Asia. And obviously in winter we have strong thermal high that develops over the interior, right? Very strong radiative cooling over that landmass. It's also snow cover that'll help the radiative cooling promote the development of high pressure, and At the surface, the winds flow from high to low. Yes, there's a Coriolis force involved as well, but what we end up generating in general is an offshore flow. Okay? Then comes summer, where we have strong solar heating. We have really, really high amounts of net shortwave radiation. Okay, and that ends up heating the landmass, like you guys said, much greater than the ocean. And what we develop is an onshore flow. And that onshore flow is highly critical for precipitation and obviously water supply of that region. So where we're going today is we'll talk about how circulation and precipitation are coupled, how circulation ends up dictating the seasonality of precipitation. For example, why in Idaho our dry season is summer, why our wet season is sort of extendo winter. Whereas how it varies very differently in a place like India. Okay, I wanted to take one step back and talk about contrast between what happens in the summertime along the east coast of the United States versus the west coast of the United States. How many people have lived along the eastern half of the country? Okay, a few people. Only 3. Okay, I can't raise my hand on that one either. But for those 3 people, in the summertime, how would you generally describe conditions? Awful. That sounds like very objective. What's that?
Literally the worst.
Literally the worst. So how about some climatological descriptors? Awful might be viewed in a variety of ways. Sticky.
Yeah.
Humid, sticky. Okay,
Greasy.
so greasy. Okay. Whereas the West Coast clearly is the best coast. West Coast is a very different situation in the summertime. Over both ocean basins, we have a subtropical high that develops in the summertime, right? Oceans are relatively cooler, relative high pressure over the ocean basins. High pressures has this sort of anticyclonic or clockwise circulation in the northern hemisphere associated with it. Also, over a high pressure, we have subsidence. Air is generally sinking. Okay. Now, along the west coast of the U.S., west coast of North America, if you look at the general direction of circulation of the flow, at the surface at least, that flow is coming from the north. So a predominant feature, a very, very reliable feature, especially if you are at the coast, say in Northern California, is northerly flow almost all the time in the summer. Okay? That northerly flow is doing a couple things. We'll talk about oceanic circulation next time, but it actually advects or moves water from relatively high latitudes where that water is quite a bit cooler down the coast. That has an effect on modulating the maritime climate, but also we're bringing in air that's coming from a much colder area. It's also much drier. So we know that the amount of water vapor that an air mass can hold is related to its temperature, and it's not linear. It looks something like this. If we just look at temperature and the maximum humidity, it looks something like this. So most of the ocean temperatures off the west coast of the United States in the summertime, what temperatures are those? Immediately off the coast. What do we think? 50? 50 is a little cold, but certainly there can be 50s out there. Somewhere between 50 and 60 if you get down to the Southern California bight, which is just south of this location here. They can get a little bit warmer than that, but not much. If you compare that with sea surface temperatures off the east coast of the United States, we have the Bermuda High here. It's got the same direction of circulation associated with it, but the east coast is on the west side of the Bermuda High. So what's happening here is it's taking air mass that's been hanging out over the Caribbean, much warmer area, advecting that northward. So it's bringing warm air northward. Ocean temperatures off the coast of the Atlantic here are easily 10 to 20 degrees Fahrenheit warmer than they are off the west coast. So that humidity is all due to this Bermuda High. Whereas the relative lack of humidity and precipitation that occurs along the west coast during the summer is due to this Pacific high, which brings cool and dry air. So the things you need for precipitation, number one, you need moisture. Number two, you need some way to allow air masses to rise. When you have warm surface conditions and you have moisture, which is typical of what you see in the eastern United States, that's the right kind of ingredients you need for convective precipitation. Whereas the West Coast, we have dry, cool conditions, relatively cool. And we also have subsidence as well, and that's going to inhibit vertical motion in the atmosphere. Okay, so now we'll move up to the middle troposphere, okay, the mid-levels of the atmosphere. This is at the 500 millibar surface. And we're looking here at the climatology, and you can see this is over a 30-year period or so. And what this is showing us here, this is just for winter, by the way, December, January, and February. So we're looking here at the heights, the elevation of the 500 millibar height surface. Right? So this is telling us a couple things. Number one, the elevation of that 500 millibar height surface is proportional to what at any given location? How high that 500 millibar height surface is proportional to temperature. Temperature of the lower troposphere. Right? So where you see warmer colors here, that's indicative of warmer air. Makes sense. It's all in the tropics. If you look at the change in the 500 millibar height across a given distance, then you're thinking about gradients. Right? And so where do we see some of the strongest gradients in 500 millibar height? Where are those contrasts the greatest? It's a little difficult. You need to do some mental math, some derivatives, spatial derivatives. They just pop, right? See, the strongest gradients are located off the eastern seaboards of the continents. So right here, off the eastern seaboard of Asia, so just from Japan out to the dateline or so, very strong gradient in height. And then likewise off the east coast of North America, we also see a very strong gradient. In the southern hemisphere, things are very much less with longitude. They're more symmetric, which makes sense. There's a relative lack of higher latitude or mid-latitude landmass. So we talked about this last time, or maybe 2 times ago, but what would be responsible for the strong gradient in geopotential height off the east coast of continents versus off the west coast of continents? Can we recall what that is? There's a couple things that come into play. Right? So the one thing is that we know that the geopotential height at any given location is more or less representative of the temperature of that air mass. Okay? And what we see is a stronger gradient in height, at least a latitudinal gradient in height, with the eastern side, the western portion of the ocean basins, east coast of continents. So that's 2 things. One, which I mentioned last time, we'll talk about more with the oceanic piece, is that the warmer waters in the ocean tend to congregate or pile up along the western boundary of ocean basins. Okay. That's actually due to the trade winds. The trade winds are blowing like this, right? So they're taking all this warm water and it's all being piled and smushed up in the western boundary of ocean basins. So, and then we have the Kuroshio current, which is bringing warm water northward. So relatively warmer air here than over here, right? These are much cooler oceans. And then if you look at the continents themselves, we have Siberia, right in here. Very, very cold in winter, strong negative energy balance. So that's where we have some of the coldest air masses. And where they meet, that ends up forming the strong gradient in geopotential height. And what does that result in? What does the strong gradient in geopotential height tell us? Strong winds, right? That's where we would expect wind speeds to be the strongest.